Okay. You said you had some specific questions?
Yeah, on 2017,
Mm-hmm.
10 and 12.
Okay, you're going to have questions like both of these, 10 and 12. In fact, 12 is going to be something like your free response. I'll show you a free response later. Your free response will be a little more difficult than 12. You might have one like 12 in the multiple choice part, but your free response will be a little more difficult. Well, let's look at 10 first. So I have these three charges. I want to know the force acting on Q2. I always like to just draw them first. And let's just draw them. So I have a force that's acting on Q2 due to Q1. That's going to be an attractive force. I'm going to call that F21. And notice I drew it a certain length. And now I want to think about the force on the other charge, or due to the other charge. And you'll find that on my test that often there's an easy way to approach the answer. That either you can get rid of answers as you're going through and find the correct answer, like there's only one obvious right answer. Sometimes you just have to work through it, but in this case you should be able to reason this one out. So I want you to notice two things. This charge is 4 times this charge, and this distance is twice this distance. And so if I write Coulomb's law, F equals KQQ over R squared, I have 4 times the charge, right, because Q3 is 4 times Q1, and I have twice the distance. So I have a 4 in the numerator, and I have a 2 squared in the denominator. So that means that F32, or F23 rather, the force on particle 2 due to particle 3 is going to be the same as F21. So I can just stop right there and say that the answer is 0. Now if you're not sure about that, like if you don't see these ratios, but I hope that you do, that this charge is 4, this force is whatever, F21. But then when I look at this force over here between these two charges, this charge is 4 times what it was over here, and it's twice as far away. And so if I have 4 times the charge, twice as far away, these two cancel out because it's dependent 1 over R squared. And so this becomes a 4, and it cancels out with that 4. So easy problem. Then if you go through it the full, like all the calculations, it's not that much more difficult. But I would say let's do 2,3. F23 is 9 times 10 to the 9th times Q2, which is 1 times 10 to the minus 6, times Q3, which is 4 times 10 to the minus 6, divided by the distance, which is 2 meters squared. And notice I get some things cancel out. This 4 cancels out with this 4. And I'm left with 9 times, so 10 to the minus 12, 10 to the 9, 10 to the minus 3 newtons. And so that's F23. Yeah.
Okay, so for your charges, you didn't put in the negatives. Is that because they're both negative, or just because it's going to cancel out anyway?
No, I never put negatives. It's a good question. So I never put negatives on these values for Q here and here. It was the same with electric field. I never put the negative. So when you're dealing with vector quantities like force and electric field, you never put the negatives. In fact, on your equation sheet, it's written a little bit differently. Let me show you. On your equation sheet, see how it's written right here? F is equal to K, Q, Q1, Q2. It has these absolute value bars. That's to remind you not to include the negatives. The same here for electric field. So you have the absolute value bars. But down here, when you're calculating potential, you're not going to see potential in this exam. But when you're calculating potential, notice no absolute value bars. The reason for that is that when you're dealing with these forces, that the negatives come into play when I'm writing the direction of the arrows, because I say like charges repel or opposite charges attract. Okay? Now, let's do F21. 9 times 10 to the 9th. Q2 was 1 times 10 to the minus 6. No negative. Q1 was 1 times 10 to the minus 6 divided by, let's see, I have something messed up here. What am I doing? Oh, times 1 divided by 1 meter squared. This just goes away. It's equal to 1, and this is equal to 9 times 10 to the minus 3. Okay? You can use your calculator for that, but notice what I did is that I have a 10 to the 9th and a 10 to the minus 12, and that's where the 10 to the minus 3 comes from. If you're good at dealing with those scientific notation, you don't ever have to pull out your calculator. If you have to use your calculator, that's okay. All right? You'll see that? I prefer you do it the easy way, where you just reason out the answer, and you'll find that on a lot of questions that you can do that. Okay? All right, let's look at the other one. Can I clear this? Yeah. Number 12, I said your free response is going to be one very similar to this. Your free response is going to be more one, and we'll look at one later, that will be something like this, where I ask you what is the electric field at that cross. In which case, it'll be different from this one, you'll see, because my electric field, let's say these are both positive, my electric field will have one vector in that direction and another vector in that direction. And the difference is that you'll have to resolve the vectors. You're definitely going to have to resolve vectors for the free response. For number 12, you don't have to do that, but you still follow some of the same procedure. I start right here. I want to know the electric field. I put my imaginary test charge right there and imagine what is the direction of the force that that test charge would feel, and then that'll be the direction of my electric field. So it's going to be repelled from this charge, and it's going to be attracted to the 32 nanocoulomb charge. I'm going to redraw it a little bit just so it's more correct. Sorry, let's see. I like to draw my vector sort of relatively correct because I want that vector to the left, and the vector going down should be 8 times the length. So it's going to be like this, something like that. Okay? So now I want to know what is the magnitude. I need to calculate the magnitude of each vector. I'll call this E1. I'll call this E2. E1 is 9 times 10 to the 9th. That's K. Coulomb's constant, times Q, which is 4 times 10 to the minus 9, it's a nanocoulomb, coulombs, divided by the distance, which is 2 meters squared. E is KQ over R squared. Look, I gave you some good cancellations here, 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 and here. So this is equal to 9. And then I know E2 is going to be 9 times 8. Y'all see how I know that? Because the distance here is the same, here and here. So R is the same, but my charge is 8 times what it is over here. So I could say right away that E2 is 8 times 9. What's 8 times 9? 72 newtons per coulomb. Well, let's just go ahead and I'll show you. If you're not sure of that, you say 9 times 10 to the 9th times Q, which is 32 times 10 to the minus 9. No sign there, absolute value of the charge divided by 2 squared. That's a 4 that cancels out up here, gives me 8. These cancel, and that gives me 72. So I have a 72 unit vector here and a 9 unit vector here, 72 and 9. To find the magnitude of that, I say the square root of 72 squared plus 9 squared. Look, I know it's going to be, well, it has to be 73. You know how I know that? So I can do this and I'll get 73, but it has to be more than 72, so it can't be that, or that. But to be 81, the two vectors would have to lie in the same plane. They'd have to lie along the same line. To be an 81 unit vector, I would have to have my 72 unit vector and my 9 unit vector. So it would look like that and that. So that would be an 81 unit vector, or 81 newtons per coulomb vector. But you can do the Pythagorean theorem, that's fine, no shame in that. And that's equal to 73. Okay? Those are good questions, and those are good tricks too. So you can move more quickly through the exam, and then you'll have more time to spend on the questions that aren't so clear to you. If you just sort of get those little mathematical tricks along the way, it'll help you a lot. Not just in this class, but in whatever you're doing in the future, GRE or MCAT or whatever standardized test or other classes that you go to. Okay? You good with those? Yeah. Tell me your name. I forget.
Peyton.
Peyton. Okay.
So for the 4 times 10 to, you put a -9. In the previous question, you put a -6.
Right. So don't forget your metric prefixes, and there are some special ones that I mean, you need to know them all, but these are the ones that you'll specifically use or especially use. Nano is 10 to the -9. Micro is 10 to the -6. I'm going to give you them all. Milli is 10 to the -3. Centi is 10 to the -2. You're not going to see any big prefixes. I won't give those to you now. Later you will, but not right now. So these are the big ones, and really we don't use milli that much. So you could need to know milli, but you definitely need to know nano, micro, and centi.
So the on and short, you just look at
Yep, you just look at the prefix right here.
that tells you.
Yeah, so it tells me that's 1 times 10 to the -6. So I sort of do that. We did that a lot last semester. I know you weren't with us last semester, but we did it a lot last semester. And so I sort of expect it to be second nature almost, that you see those prefixes and that you know right away. I know that's not true for much of the class, but I want you to know those prefixes pretty cold. Sure. Oh yeah, so 13, I don't really need to do any calculations because I know, because you drew the vectors here relatively to the right size, this is a small vector, this is a big vector, I can tell you sort of, well, it's not B, it's not C, it's not D, it's not E, it has to be A. In fact, A is the only one that's below the negative x-axis. And so I know that this resultant vector lies right there. Remember, with vectors, you can move them around. So I can take the vector that I had here and translate it over here, and then I do my tip to tail, where I start, or my tail to tip, excuse me. I start at the tail of the first vector, and I draw the resultant to the tip of the second vector. Notice this right triangle right here, and I want to know what this angle is. And so if I want to know that angle, I'll call it theta. It is the inverse tan, let's see, SOHCAHTOA, opposite over adjacent. The opposite side is the 72 side, and the adjacent side is 9. So 72 over 9. And if I do that, y'all can check me, but it should be 83 degrees. That's the only answer that makes any sense. When you do that, make sure, be careful with your calculator. First of all, make sure you're in degree mode. If you're in calculus, you might be going back and forth between degree and radian mode. And also, be careful with the signs. You need to practice with this. I recommend always that you draw a picture, because the picture will help you. Was that right?
Mm-hmm.
Yeah. The picture will help you to figure out the answer without having to use your calculator at all. Because I know it's in the third quadrant, that vector. So this is the only angle that gives me the third quadrant. But also, if you put signs in your trig function, like y'all have pretty fancy TIs, they might be smart enough to tell you what quadrant it is in, but sometimes it's not smart enough. Let me show you what I mean. It's, like here, I have an x component in that direction, and I have a y component in this direction. If I put in my signs for these, which are -9 and -72, your calculator might do one of two things. It might say, oh, that vector is in the third quadrant. But your calculator could also say, oh, that vector, because the two negatives cancel out, is in the first quadrant. Some calculators are fancy, and if you put the negative in the right part of the fraction, either opposite over adjacent, it recognizes what angle is. That's all to say, just draw a picture. That's the easiest way to do it. You're more likely to get the answer right if you draw a picture. Okay? All right. What else we got? Does that help a little bit? We're going to see some more. We're going to do this in class on Wednesday, and we'll do it again on Thursday, I'm sure. It's probably the hardest part of this exam. Any particular questions we can look at? If not, I have some. You want to hear my questions? At number 14, you're going to see a field problem, like number 14, where I ask you the charge or I ask you something about the electric field. They're not that hard once you get the hang of it. So here I have two spheres. I tell you that Q2 has a charge of 4 coulombs. And then I'm asked for the charge of Q1. First of all, I know that Q1 is positive or negative? Is positive because field lines always come out of the positive charge. So I know this is positive and this is negative. They always end in a negative charge and begin in a positive charge. And I know that Q1 is bigger or smaller than Q2. It's bigger. So oh shoot, look, there's the answer. I don't even have to really think about it that much, just by asking those two simple questions. But in some cases, you might have to think about it a little bit. So I have 1, 2, 3, 4 field lines going into the 4 coulomb charge. You can think about it in this way. I like to think of how much is each field line worth. And in order to figure that out, I say the charge, 4 coulombs, divided by the number of field lines. So it's like 4 coulombs divided by 4 lines. That tells me that each line is like it's worth 1 coulomb of charge. 1 coulomb per line. And now I go over here and I say, okay, I have 1, 2, 3, 4, 5, 6 charges over here, or 6 lines. So that means if I have 1 coulomb per line, then it has to be 6 coulombs. I think you probably could have worked that out here, just not having to do that ratio. But sometimes this number is not a whole number, like it's a decimal number, and you might need to do this more thoroughly to figure out what is the charge. But often you can whittle it down to just 1 or 2 choices just by saying, okay, what is it not? And answering that question will help you a lot. Yeah. So.
I have a specific question from the quiz.
Yeah.
I don't know if we can go over those.
Yeah, of course. The quiz questions are on the old exams. I don't give the quizzes back, but the questions are out there. I like to keep those quizzes. I don't know, because I read them at night. No, I don't. So what's the question?
I don't know.
Can you just sort of give me
I think it was like the second to last one. You were solving for the charge on something relating to the charge. I think it was the second to last question of the quiz.
All right, give me just a second. I just need about 30 seconds. All right. Oh, this question right here?
11.
Number 11. If the distance is 10 meters, what is the net electric field at a point equidistant?
Yes, it wasn't charged, but yeah, that's the one I'm thinking of.
Okay, let's take a look. I'm going to redraw it. Can I draw in this? That I can. Let's see if I can. Oh, I can. Okay. So if the distance is 10 meters, I want to know what is the electric field at a point that's right there. First of all, draw my electric field vectors. I'm going to call E1 the one due to the Q1, so it's going to be E1 is in this direction, and then E2 is going to be in that direction. Notice I drew E2. Actually, it's 1/50th of E1 because the charge is 1/50th of Q1. So I can get rid of one answer. That's definitely not the answer because it's to the right. E1 is to the right, and it's the dominant vector. And then if I want to know the net electric field, I can calculate E1 is KQ over R squared. I'll show you an easier way how to do this just a second. 9 times 10 to the 9th. Q was 50 times 10 to the minus 6 divided by the distance, which is 5 meters squared. That's 25, so that gives me 2. That cancels and gives me 10 to the 3rd. So it's 118 times 10 to the 3rd. Okay? And then if you calculated E2, you find that E2 is, well, 1/50th of that, right? And so the answer is, because 18,000 is so much bigger than 1/50th of 18,000, is going to be A, 18,000. Really what I need to do is calculate E2, and it's going to be 18 times 10 to the third divided by 50, whatever that is. I don't know what that is. And then you would subtract those two numbers. E1 minus E2 is equal to the answer. But because that number is so much smaller, it's just going to fall out in the sig figs.
4.5 times 10 to the negative third.
Okay. 4.5 times what?
10 to the negative third. Oh, no. No.
Like 450. I don't know. It's small. Small compared to 18,000. Okay? Another way that you could do this, like if the charges were not so different, because they're equidistant, because they're the same distance, the point in the middle is the same distance between the two charges, another way that I could do this is I could say that E, not E1, not E2, but the total E is equal to K times 49 times 10 to the minus 6 divided by 5 squared. And then that would give me my answer, which would be about 18,000, something less. You see what I did there? I subtracted the two charges. That only works if it's equidistant, which happens, frequently in the exams. It's just a way to make the math a little easier, but still test you on the physics. You want to look at the rest of the quiz? Do you have any? Quiz was tough. I was expecting, I don't know what I expected. I expected better scores. I really did. But that's okay. We'll pick up and move on.
Over 12.
Yeah. Okay, so 12 is conservation of charge. I start out with minus 3 coulombs. I have to finish with minus 3 coulombs. So that means this has to be minus 4. Because minus 4 plus 1 is minus 3. Good questions. See them Friday. What else on this quiz? Well, number 8 was really similar to number 11. Number 10 asks, where is the electric field greatest? You have to think about the relative sizes of the vectors. I forget what the answer was here, but let's look at number 10, because these are useful thought problems to help you think about electric fields. I just draw out the vectors for each one. So at point A, we'll do this in red. I'll do the electric field, do that in blue. I have one vector that's in that direction, because if I put a positive charge there, it's going to feel a force that's repelled by the plus 2q. And then I have another vector that is twice as big in this direction, because it's attracted to that minus 4q. It's twice as big because that charge is twice as big, and yet this point in the middle is the same distance between these 2 points. Okay, so where's the electric field greatest? That's a pretty good contender. Let's look at the other one. Due to the plus 2q, I'm going to feel a force, I feel a force that's opposite, that's repulsive, and it's going to be a lot smaller than I drew it over here. In fact, it's going to be 1/9 what I drew over here, because look, this is one distance from here to here, and I have 1, 2, 3 times that distance from here to there. So because it's 3 times that distance, it's 1/9. So I drew that vector small. I really need to draw it smaller. And then the other is going to be, well, it's going to be the same. So it's the same as the first blue vector that I drew. So A is the bigger one. That's the bigger electric field. I have 2 vectors in the same direction. You see a lot of those questions on my old exam, so make sure you know how to do that. You'll definitely have one. You had several on this exam. All right. Any of these others stand out to you? Which one to look at? Number 3? Yeah, so where on the x-axis can a third positive charge be placed such that the net force on the charge is 0? So I really only have 3 possibilities: to the left of Q, in between them, or to the right of 3Q, like here, here, or here, somewhere in those regions. So I just take each one and I draw the vectors. I'll do this charge in blue, this charge in red. So over here, I'm looking for a positive charge, and I want the force on it to be 0. So if I put a positive charge, it feels attracted to the minus q, and then it feels repelled from the 3q. And then over here, in the middle, it feels attracted to the minus q and repelled from the 3q. Oop, that's to be red. So I can automatically get rid of this one because those two vectors are in the same direction. No way to get a net force of 0. It is possible on the left to get a net force of 0, but we'll see. Like I know what the answer is, but we're not fully convinced yet. And then on the right side, over here, if I have a positive charge, let's see, it's going to be repelled from the 3q. That should be red, I'm sorry. Repelled from the 3q and attracted to the minus q. I drew this vector a little too long. So on both sides, on the left and the right, I have vectors that are opposite one another. So what becomes important is the sizes of those vectors. And in general, in these problems, when you're trying to find a place where the force or the electric field is 0, you're trying to get far away from the big charge. Because by getting far away from the bigger charge, it's like you're minimizing the effect of the bigger charge by increasing the distance. And that's what I've done here. So what do y'all think the answer is? Really? It is to the left, yeah. So yeah, and I drew the vectors here pretty close to what they are. These are equal but opposite vectors, but there's no way to get equal but opposite vectors on this side. Like no matter where I am over here, because I'm always going to be closer to the big charge.
Okay, I was thinking since I had 3, it had to be, I guess the q would be farther away.
Yeah.
Or something.
So let me say again. So I want these two vectors.
I was thinking the negative had to be, I guess, triple to equal the 3. You know what I'm saying?
Yeah, I think I understand. But I want these two vectors to be equal but opposite for 0 force.
Okay.
And if I get closer to the 3q charge, this vector gets a lot bigger, the red vector, but the blue vector just gets a little bit bigger. But over here, because I'm so far away from the 3q charge, which is a bigger charge, I get a smaller vector here than I do over here. So in general, on these questions, when you're looking for 0 force or 0 electric field, get away from the big charge. Drawing the picture always helps. Like that's almost always what you have to do. I can sort of look at it and think about it, but it really have to draw the picture to think about what happens. Are you asking a question?
Yes. So if that was just the positive, or would it not be set up like that?
Which positive q?
The 3, if it wasn't a 3 and it was just the positive.
Oh yeah, if it was a positive q, good question. What would the answer be? I don't think it'd be possible. So yeah, so let's just try that out. So if I had a minus q, it's a good question for the test, and a plus q, where could I put a positive charge? Well, look, if I put it over here, a positive charge there, we'll do this blue. I'm attracted to that one, and I'm repelled, but not very much by the other one because I'm far away. I can't get a 0 force there, right? Here in the middle, if I put it here, I'm attracted to the negative, but I'm repelled from the positive. Can't get a 0 force there. Nowhere in the middle can I get a 0 force. And then likewise, on the other side, if I'm over here, I'm attracted to the negative charge. Wait, no, this one was positive, wasn't it? I would be repelled from that charge and attracted, but not very much, to the other charge because I'm farther away from it. I was letting this negative right here be blue and this positive right here be red in those vectors. So not possible. The answer would be D for that one. There's no place where I can put a positive charge and have 0 force on it along the line. There is a place above the line somewhere, and It's not hard. It's not trivial to find that point, but on the line, you can just think about it. Okay? Be ready for those kinds of questions. You're absolutely going to have them. In fact, you probably have more than you usually do. I like those kinds of questions because it really shows that you understand how the fields and forces work. And because we only have chapter 1 on this test, I have more opportunity to ask you those questions. I don't want to, like, I'm not going to add a whole bunch of calculation problems because you can either do them or you can't. You'll have a few, but I'm not going to fill in that space with calculation problems. I'm going to fill them in with problems like this. Y'all understand, right? Like, usually I have chapter 1 and part of chapter 2 on the exam, but now it's just chapter 1, which is good for you because there's just less material. And it's good for me too because I get to ask more questions. Everybody wins. Okay? What else? The what? Sure. I like that one. So here we're drawing the vectors again. So if I have, I'm going to start with a 5Q and go around clockwise. I have a relatively big vector from the 5Q. It's attracted because I have opposite charges. A smaller vector for the 2Q. The negative 5Q, I'm repelled. And the plus 2Q, I am repelled, like that. Oh, wait, no, I'm attracted. Never mind. Not repelled, attracted. So these two forces cancel one another out because I have two like forces, and so the answer is quadrant 2. Okay? Y'all can do those, right? It's really about vectors. That's why this chapter is so hard, because it's all about vectors. But vectors are very, very important in physics, and I want to make sure that y'all know that. All right, what else? We can do a few more. I will do as many as y'all want, but if I'm okay. Oh, goodness. No, that's not what I wanted. Clear. Okay. Yeah, it was a nasty sound. Do y'all want to do a problem like the free response? Okay, let me show you. I've only been doing free response in this class 1 semester, so give you a good feel, the exam 1 from last year. And it will be a lot like this problem. I might move the charges around a little bit, but it will always be so that I have one charge, one electric field on axis and one off axis. So, the way you do this is you draw your coordinate system. It's right there, and I label my vectors. E2 is going to be in this direction, and then E1 is in this direction. I know E2 is towards Q2 because if I imagine my positive test charge at point A, it will be attracted to Q2. If I put my positive test charge at point A, it will be repelled from Q1. So E2 and E1 are there. Now I need to calculate E1. It's going to be 9 times 10 to the 9th times 9 times 10 to the minus 9. That's Q1 divided by the distance. This distance is 3 meters. 3 squared. I get lots of cancels here. There, 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 and there. And it leaves 9 newtons per coulomb. Did I work this in class today? I worked one really similar to it. Yeah. And then E2 is really similar. 9 times 10 to the 9th. That's K. Q2 is 25 times 10 to the minus 9. No sign, no negative sign there, even though it's a negative charge. Absolute value. Divided by this distance right here. Know your triangles. This triangle is 3, 4, 5. You'll probably have a 3, 4, 5 triangle. So I think y'all know how to do the Pythagorean theorem, but it's just 3 squared plus 4 squared. That's equal to 5. Divided by then 5 squared. Cancels, 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 and it leaves me with 9. So I'm going to redraw my vectors again. If you're not sure, draw a picture. It will help you. I have one vector here that is 9 units long. and another vector here that's 9 units long. Now I also need to figure out what is this angle right here, which on this triangle is the same angle as right there. You don't know what that angle is? No, it's opposite the big side. 53, right? 37 is the small angle. So this angle is 53 degrees. I would find it by saying the inverse tan of 4 over 3. That's 53 degrees. SOHCAHTOA. Okay? The other angle is 37. So that means this angle is 37 degrees. Step 1, all done. Step 2, resolve the vectors. I'm going to do it on a coordinate system, so it just sort of we see it. I have 9 right here. Here I have 9 cosine 37. That's 7.18. I would say 7.2. And up here I have 9 sine of 37, which is 5.4. The other triangle that I like to give is the 30, 60, 90 triangle, by the way. Those are really the only 2 triangles. Or you might see an equilateral triangle. But those 3 triangles, equilateral right triangle, 30, 60, 90, that means a triangle that is 30 degrees, 60 degrees, because those sine and cosine functions work out really even. One of them's a half. Are an equilateral right triangle, where these 2 sides are equal. And so these angles are 45 degrees. But know your quadratic, know your trig functions, and you'll never go wrong. Okay, so now that's step 2. Step 3 is add our vectors. So this one is 5.4. There's nothing to add it to. This one is 9 minus 7.2, which is 1.8. Oops. Now, step 4 is to find the resultant and the magnitude and direction of the resultant. I like to redraw these triangles. There's 1.8. There's 5.4. So I'm looking for this vector. Notice that's a right triangle. I want to know that angle. Theta is the inverse tan. 5.4 over 1.8. So inverse tan of 3. 72 degrees. That jives with what I think it should be, because the way I've drawn those vectors, that's a really big angle. It's bigger than 45. And then also, I want to know what is this side of the triangle. And so the electric field is the square root of 5.4 plus 1.8. Squared, both of them. Make sure you're practicing that on your calculator, that you know how to do that. Get your order of operations and all that right. It's 5.7. That's the answer, 5.7 newtons per coulomb, 72 degrees. Where is it? It's above the positive x. See, because it's right here, that angle right there. That would be a couple of parts. It might be 3 parts to the question to get to those answers. Like along the way, I might ask you, what is the x component or something? I don't know. But I like to give, those of you who haven't had me, and you have me, but you didn't have these types of questions. What was I going to say? I give multiple questions as you get to the answer. If you get one of those wrong, and then that inhibits you from getting it right on the other parts, I don't count off for those other parts. But you have to show your work so I can tell that you actually know what you're doing. With the free response, you can get all the credit. I just go through and I see, who has the right answer and who showed their work. Boom, boom, boom. Those are all full credit. Those who get no credit, if you don't show anything, obviously that's no credit. Or if it's just obviously wrong, your approach, then you'll get no credit. But if you have something in between, you can get half credit. Okay? The students benefit from this. So I felt like it was a good thing for the students last semester. It adds a lot to the grading, but I think it's good. Okay? questions about this? You're going to see this again. We're going to do it on Wednesday. We'll do it on Thursday. So you will see this again. It'll be a big part of the exam. 3 or 4 questions. That's 9 to 12 points on the exam. All right. Anything else? Or is that too much? Any other specific questions? General? All right. We can wrap up if y'all want. Were you raising your hand? No. Okay. We'll wrap up there then. So we're